This is Lecture 1 of Module 7 in the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is Introduction to Statics. In the previous modules, all of the motion was pure translational. When the motion is pure translational, the object can be treated as point masses, and we did this in many cases. So here's a car, let's treat it as a point mass. We're assuming it's not going to roll. In the next module, we're going to investigate rotational motion. It is not rotational motion instead of translational motion. It is rotational motion in addition to translational motion. Everything we did previously is still valid. The vector sum of the forces on an object is still ma for that object. Energy is conserved, momentum is conserved. So let's think about this situation. A puck is heading toward a stationary stick on a frictionless table. The stick is just lying there. It's not attached to anything. This is the top view. There is the center of mass of the stick. What happens when the puck hits the stick? Well, the stick is going to translate. The center of mass is going to move, and it's going to spin. It's going to rotate clockwise. It's a complicated problem. When we do conservation of a momentum, we ignore the rotational motion of the stick. It's just mv as always. M puck, v initial puck, that's the initial momentum. The final momentum, we have the puck moving and we have the stick moving. That cm means center of mass. If the stick is heavy relative to the puck can bounce backwards. We can imagine the puck bouncing backwards. If the stick is light relative to the puck is going to keep going straight. If the puck impacts the stick closer to the center of mass, it's going to spin less. Further away from the center of mass, it's going to spin more. We're going to investigate all of this in the next chapter. I'm just mentioning it here to emphasize that rotational motion doesn't take the place of translational motion. Everything is still valid. Now, when this stick is spinning, calculating its kinetic energy is going to be a challenge because the different pieces are moving at different speeds. That's going to be fun. Here, in this module, we're going to only consider static situations. Nothing is happening. Nothing is moving, nothing is accelerating. The sum of the forces on every object is going to be zero. We're going to see that this is not enough to solve problems in which the objects can't be considered point masses. So here's a situation. A 12-foot plank has a weight of 24 pounds, rests on two sawhorses. The sawhorses are each 1 foot from the end. Plank weighs 24 pounds, 12 feet long. We know gravity is pulling down on the board with the force of 24 pounds. That's what weight means. Gravity is exerting a 24-pound force on it. The sawhorses have to be holding up that weight, and since they're symmetric, they're both 1 foot from the end, we can assume that the sawhorses are each pushing up with a force of 12 pounds, and we would be right. That's what's happening. What happens when the sawhorses are not symmetrically placed? Like this. Let's move this one in a little bit towards the middle. All right. What happens now? We know that these two forces, these two sawhorses, have to be pushing with a total of 24 pounds, but we don't know the value of each. Is it 10 and 14, 14 and 10, 8 and 16? We need another equation. And that equation comes from the fact that the plank is not rotating. There's no angular acceleration. It's just sitting there. If the object is in rotational equilibrium, the sum of the torques on it is zero. If it's in translational equilibrium, the sum of the forces on it is zero. So that's a torque, lowercase Greek tau. A non-force net force causes an acceleration. A non-zero net force, a non-zero torque, causes a rotational acceleration. So let's explore torques a bit before we tackle this problem. I'm not even going to read this because it's confusing. Well, maybe I will. The magnitude of the torque exerted by a force about the axis of rotation is the product of the distance between the force and the rotation axis and the component of that force that's perpendicular to that distance. And maybe I shouldn't have read it. To see what this means, consider a propeller mounted on an axle. So there's a propeller, it's mounted on an axle, and we're going to put a force on it to rotate it. Here's F1. pushing here. What's the torque produced by this force? We need to know how far it is away. Let's put that in. There's the axis of rotation, this gray dot. That's the distance away. And this is the force. Now, all of F1 is rotating it. It's at a right angle to the distance. So F1 is already perpendicular to the distance. So the torque is just F1 x1. How big is the force? How big is the distance? If you want to spin something, you try to go far away from the axis to produce a bigger torque. If it's the same force, the farther away you get from the axis, the bigger the torque. If you push with the force in here, it's hard to get that propeller spinning. You have to push on the outside. So it makes sense that the torque is the magnitude of the force that's perpendicular to the distance times the distance. How about F2? Here's F2. This person trying to spin the propeller by pushing like that. Now it's certainly a distance away from the axis, but it has no perpendicular component. It's along x2. There's no component of F2 that's perpendicular to x2. So the perpendicular component of F2 is 0. So the torque is 0, right? It makes sense. It's not going to spin if you push on it like that. So now let's return to the problem with the plank and the two sawhorses. There we go. Let's put some numbers here. The plank is 12 feet long. The sawhorse on the left is 3 feet from the end. The sawhorse on the right is 1 foot from the end. That's 4 feet total. The distance between the sawhorse is 8 feet because the total length is 12 feet. Now we can think. This class is not about transferring knowledge. It's about providing opportunities for the students to develop the ability to figure things out for themselves. Physics is a great playing field to develop your thinking skills, to independently reach a new level of understanding, to have the aha moment. Ah, yeah, I see how that works now. This is a great opportunity. So you should stop the video, think hard about which of the two sawhorses, if either, is supporting more than 12 pounds, which is half of the 24-pound plank. So during the exams, you'll need to think hard about the questions, and you're not going to be able to scroll ahead to the answer. The way to develop the skill to think hard about questions is to practice. If your goal is to do well in the exams, start thinking practice right now. Give it a good shot. Which one of those two sawhorses is pushing up with a bigger force? Okay. It should eventually become clear that the sawhorse closer to the center is supporting more of the weight. Easy way to see this is to just slide it in close to the center. When it's there at the center, you don't even need this one. It'll balance right there. If it's in the center, it's going to be holding up all of the 24 pounds. So let's calculate how much this sawhorse is pushing up on the plank and how much this sawhorse is pushing up on the plank. Let's get quantitative. It's a statics problem. Nothing is happening. There is no particular point of rotation. We can pick any point we want as the point of rotation. It's not rotating about any point. The natural point to use is the center of the board. This is not the most efficient choice, but that's okay. We're not trying to be as efficient as possible. We're trying to understand what torque means. We want a fundamental understanding of the concept of torque. So if you're not yet a Jedi Master at identifying forces and drawing force diagrams, you should be by now, but now you're going to get more practice. It's the same thing. We're drawing force diagrams. What are the forces on the board? There are 3 forces on the board. The normal force from the left sawhorse, it's pushing up on the plank. The normal force from the right sawhorse, that's pushing up, and gravity is pulling down at the center of mass with 24 pounds, the weight of the plank. The 2 normal forces must sum to 24 pounds. We know that. We have 2 knowns and we have 1 equation. The equation is the sum of the forces in the y direction is ma sub y, and a sub y is 0. So let's take torques about the center of the board. When doing statics problems, you have to choose a point to take torques about, and it's useful to really boldly, unambiguously label this point so you do not forget what you're doing. So let's put a big red splotch there. There is our axis of rotation. We're going to see which forces rotate the plank about that axis, and we're going to calculate the torques from them. The gravitational force does not exert a torque about the center of the plank. If you pull on the plank here, if there's an axis there, it's not going to rotate. There's no distance away. The normal force from the left sawhorse exerts a clockwise torque. This force is going to rotate the plank clockwise about this point. The normal force from the right sawhorse is exerting a counterclockwise torque about the center of the plank. And since the plank is static, these torques must balance. The torque from the left sawhorse, we need the distance. How far is this away? 3 feet. Total plank is 6 feet. The center of mass is total of the length of the plank is 12 feet. That's 6 feet. That's 3 feet. So the torque counterclockwise is the normal force from the left sawhorse times 3 feet. Right sawhorse, half of it is 6 feet. That's 1 foot. That's 5 feet. So the normal force from the right sawhorse times 5 feet is the counterclockwise torque. We have one torque spinning it counterclockwise. We have one torque spinning it clockwise. It ain't spinning. Those torques must balance. We can set them equal. So we set these equal, divide by 5 feet, divide by 3 feet, solve for the normal force from the left, and we get the normal force from the left is 5/3, the normal force from the right. From the sum of the forces in the vertical direction, we know that they have to sum to 24 pounds. We can substitute in the expression for the normal force on the left, and we get 24 pounds. 5/3 plus 3/3 is 8/3. And we can get a common denominator and solve for the normal force from the right, and we get 9 pounds, 3 times 3. This means that the other one has to be 15 because they have to sum to 24. So this is bigger as we expected. So let's take torques about some other points to really hammer home the concept of torques. Let's take torques about the point where the left sawhorse contacts the plank, right here. So now we're going to move the red dot over here to remind us that we're taking torques about this point now. The normal force from the sawhorse on the left exerts no torque about this point. The gravitational force is clockwise. The normal force from the right plank is counterclockwise, and those torques have to balance. To get the torques, we need the distances. The gravitational force is 3 feet away. So the gravitational force is mg times 3 feet, which is 24 pounds times 3 feet. The counterclockwise torque from the right sawhorse, we need that distance. That looks like 8 feet. 8 feet times the normal force from the right sawhorse. Setting these equal. Dividing by 8 feet, we get normal force from the right sawhorse is 9 pounds, which we got previously. By taking torques about one of the unknowns, we got the answer in one equation. Before, we had to use 2 equations and 2 unknowns because we took torques about gravity and we had 2 unknowns. If we take torques about this point, this force does not appear. So we only have one unknown. So that's a little shortcut. We know that this is 15 pounds already, but let's calculate it by taking torques about the right sawhorse. Here. Now we're going to take torques about this point. Note that gravitational force exerts a clockwise torque about this point and a counterclockwise torque about this point. The force of gravity is rotating the plank counterclockwise around this point. The normal force on the left sawhorse is clockwise about this point. So let's take torques about that point. We have to unambiguously label that point and take care to get the distances correct. Be careful. So this is 8 feet away times F normal from the left sawhorse. That's the clockwise torque. Gravity is 5 feet away from the point at which we're taking torques about now. And we can set these equal, plug in 24 pounds for mg, and we get this force from the left sawhorse is 15 pounds, which we knew already. So now we know that the normal force from the left sawhorse is 15, the normal force from the right sawhorse is 9, and gravity is 24. Let's do something really different. Let's confirm we can take torques about any point, and let's choose the left end of the board. Right there. Now we're going to take torques about this point. Now all three forces exert torques. The gravitational force is clockwise, and these two are counterclockwise. We have to get all the distances from this point, the point we're taking torques about. The clockwise torque from gravity is 6 feet times 24 pounds, which is 144 foot-pounds. That's a torque, force times distance. The counterclockwise torque, we have two forces producing counterclockwise torques. The normal force on the left sawhorse is 3 feet away. The normal force on the right sawhorse is 11 feet away. Right? Okay. The counterclockwise torque is 3 feet times the normal force on the left sawhorse, 11 feet times the normal force from the right sawhorse. And we know those forces already. 15 pounds is 3 feet away. That's 45 foot-pounds. 9 pounds is 11 feet away. That's 99 foot-pounds. 45 foot-pounds plus 99 foot-pounds is 144 foot-pounds, which is the clockwise torque. So it's not going to rotate because the counterclockwise torque equals the clockwise torque about any point you want to choose. Plank's not going to rotate. We know it's not going to rotate. So how about practicing by taking torques about the right end of the board? That's good practice. In this lecture, the introductory lecture, all of the forces are at right angles to the distances, right? Here's the distance, 3 feet. The force is perpendicular to that, so right angle. Gravitational force, right angle. This normal force, a right angle to the distance. The distances are along here. The forces are all perpendicular to the board. And in the next lecture, we're going to consider situations in which the force and the distance are not orthogonal. We're going to have to get a component of the force. Here's an example, 714 in the textbook. We have a beam that's held up by a rope. The rope's at 37 degrees, and there's some mass hanging from the end of the beam. What's the tension in this cable? Nice problem.